galaxy formation in the cosmic ecosystem. And today, so the first time we talked about the cosmological context, of course, and the second day or second lecture, we talked about galaxy growth, how galaxies grow out of these primordial fluctuations and the various processes that self-regulate galaxy growth. But now, of course, you get a little later on in life and you start worrying about when you're going to die, right? And so now we're going to worry about when galaxies are dying, right? And what we mean by dying is that they stop their star formation roughly and become what we call quenched. Okay, so again, just to sort of recap, this low mass end we've seen is reasonably, at least plausibly explained by feedback associated with star formation, right? So the inefficiency here, the dropping efficiency of of star formation is that supernovae plus perhaps some other things that we're not quite sure of yet, stellar winds or cosmic rays. There are many possibilities, is increasingly affecting the low mass galaxies, and that's why they have a lower efficiency of star formation as you go to lower masses, right, in terms of halo mass here. So that's very good. The problem is, of course, that this doesn't extrapolate, right? Remember that we computed a simple model which puts you up around 0.1, and we never even get close to that before we turn around and start going down again, right? And not only that, that turn down is accompanied by a number of global changes to the overall galaxy population. As you probably know, these things tend to be sort of star-forming disk-y things with lots of gas and dust, cold gas and dust, and these tend to be quenched, obviously more massive, ellipticals, etc., right? One of the interesting facts about these is that these tend to have fairly small black holes for their particular stellar mass or their the amount of stars they have, whereas these ones tend to have fairly massive black holes, and that's of course going to be a big clue as to what's going on. So we developed this simple model last time, this kind of idea of this equilibrium with gas coming in and then getting blown out and some of it recycled, and we wrote down some very simple equations for that. And at the massive end, if you remember, right, there was this very strong truncation, that basically galaxy formation becomes inefficient above about 10 to the 12 in halo mass. And it's not supernovae, because as we calculated, the supernovae don't have enough energy to blow stuff out at that. On top of which, there's not a lot of supernovae here because they're red and dead, so there isn't much star formation. So we can't appeal to that. So we have to look around and go, well, what's left to give us energy? That we're going to need a lot of energy here, right? We saw we need a lot of supernova energy. These things are even more massive, right? What's going on there? And so I think essentially every black hole or every galaxy formation theorist has come to the conclusion that we need to somehow extract energy from the black hole, right? And fortunately, we see this. We see these black holes go active from time to time and become AGN, right? Active galactic nuclei. So there's some interesting things that you can sort of learn by studying the overall demographics of the relationship between black holes and galaxies, right? So one of the things you can look at, as we saw this plot earlier, this is this sort of Maddow plot. In fact, this plot is from the Maddow and Dickinson review. What's interesting, so this is in this case, the star formation rate or the black hole growth rate density versus redshift, right? So the black one was what we talked about last time, that star formation, starts off low as things are small, and then they grows as the galaxies get bigger and bigger, but eventually it kind of turns over, right? Interestingly, the black hole accretion rate basically follows this, except scaled down by a large value. And in this paper, they claim the value is around 3,000, right? So basically, if you look at the various determinations of this black hole accretion rate density, the form looks very similar to the cosmic star formation rate, But of course, all of these numbers have been multiplied by a large number because, of course, black holes are much smaller than the galaxies. So that's pretty interesting, right? It tells you that galaxies and black holes are kind of co-growing, one would think, right? You can also see a very clear connection between the black hole mass and, let's say, the stellar velocity dispersion or the stellar mass, okay? And this one in particular is known as the famous Megorian relation, which essentially argues that there's a power law dependence over many orders of magnitude in black hole mass between the mass of the black hole versus the velocity dispersion of the galaxy. Now, what's special about the velocity dispersion? Well, the velocity dispersion, right, is for an elliptical galaxy, the velocity dispersion is just the velocity of pretty much all the stuff. But for a spiral galaxy, of course, the velocity dispersion is really only tracing the bulge, right? The rest of it is rotation support. So this is really telling us that the black hole mass traces the bulge mass, better than the overall stellar mass, and you can see it in this plot as well, right? So this is, if we do plot it versus stellar mass, what we see is that these blue things here, or these are kind of early type galaxies, so ellipticals, S or S0s, they lie along this fairly high relation, but once you get to sort of lower mass systems, the star-forming galaxies tend to be more down here, right? And so yeah, this is basically, there is clearly a connection between the massive black hole, and the question then becomes, what is the relationship between the two? Is it that the black hole affects the galaxy in some way? Is it the galaxy affects the black hole, or somehow they're just both responding to some overall similar process, right? And it's just coincidence. One of the things is that you can see today, at least, is that strong AGN are often associated with galaxy mergers. So this is an example of that, right? So NGC 6240, this is clearly a merging system. It's a big train wreck. It has both a starburst and an AGN, right? Now you would say that, okay, if we just sort of extrapolate this idea that, that black holes grow whenever you have mergers, that would be okay, but it would not really be consistent with this. And there's a bit of a logic here, and I won't go through all the details of it, but essentially the basic idea is this. We know the star formation rate, I showed you last time, is not dominated by mergers, right? The star formation rate is maybe at most 10%, maybe 20%, depending on how generous you are with what you call a merger, right, of this, and essentially at any epoch, right? So it's just weird that the black hole accretion rate would follow that exactly, or very close to it, if it was only occurring in the mergers, right? You see what I'm saying? Right, it would be a massive, weird coincidence, right? There are better arguments against that, but that's roughly true. And essentially, the interesting thing is that this connection, this strong connection between mergers, starbursts, and AGN, only seems to be true since a redshift of a half or so, right? You go to higher redshifts, it's not obvious that mergers preferentially give rise to black holes, or black holes AGN preferentially live in mergers. So it's a complicated relationship, but generally, it seems that black holes are related to galaxies, but they sort of grow with the galaxies, right? So how does this work? So how do black holes grow? Okay. So just to kind of give you a schematic of how things work, right? We won't go into this too much, but you have your black hole here, and for the same reason we had galaxy disk, you get an accretion disk around the black hole, right? So you have this accretion disk of gas and possibly dust as well, most likely dust. And so the black hole can then, as it's accreting, it can release some energy, right, due to just converting, essentially, once you accelerate the stuff in the black hole disk, you get enough energy that you start generating, particularly hard photons like X-rays and UV, and this can push back against the gas that's trying to fall in, right? So there's this competition between the two, and I like to say black holes are very messy eaters, right? They don't eat a lot of what's put on their plate. Maybe 5 or 10%, that's it, right? The rest gets somehow chucked out somewhere, right? these processes can be, this is what's called a torus, right? Can have sort of different relationships, and this turns out to be very, very important for how efficiently black holes can accrete. So there's several sort of, just like we had this kind of cold mode halos versus hot mode halos before, we have sort of cold accretion and hot accretion onto black holes, right? And in a cold accretion case, what happens is that this disk is so dense that the cooling is so fast that essentially it can reach all the way down. The slim disk can reach basically all the way down to where the black hole can actually accrete it. So maybe there's a small boundary layer here, but this sort of cold mode, just like cold mode galaxies, cold mode accretion in the black holes is also very efficient, right? And you can get very high accretion rates from that. But it turns out that as that accretion rate drops down, you get a sort of a phase transition. And that phase transition results in, instead of having this cold material be able to get all the way down to the disk, again, in good analogy with the halos, right, what happens is that it instead forms a sort of a hot, thick, hot torus, right? So essentially the cooling isn't fast enough because the density is lower here, and as a result, the accretion becomes much less efficient, okay? And there's this, I won't go into what exactly that is, but there's this thing called the advection-dominated accretion flow. And essentially what it means is that once you end up in this hot state, right, you can't just funnel in anymore. You have to sort of advect the material in and it's much more slow, okay? And this is why essentially these result in much lower accretion rates, right? Or even you can even pretty much shut off the black hole altogether if these things are too large, right? So the way a variety of both observational and theoretical considerations suggest that this transition between this efficient mode and this less efficient mode occurs at an Eddington ratio of about a couple percent, 1 or 2%, all right? What is that? What do I mean by Eddington ratio, okay? So if you remember, there is any system that's putting out some luminosity has an Eddington rate, right? And an Eddington rate is essentially a balance between gravity pulling things in and photon pressure effectively being able to push things out, right? And so it depends on the luminosity, and it just basically it scales with the black hole mass, okay? So each black hole has an Eddington rate, and when it's in a high Eddington rate mode, it's sort of, it's in this kind of mode, and then it goes to a low Eddington rate, and this transition happens at around 1% or so. Now, here's where things get really interesting for galaxies. Not only does the character of the accretion disk change, but the character of the way that the black holes release their energy changes, okay? So it's kind of depicted here a little bit, where when you have this very high accretion state, right, you start blowing this radiation out, right, due to essentially it creates this radiation, and you have these, what happens is that effectively the radiation pressure blows stuff off the edges of the accretion disk, right, kind of like, blowing a hot wind over a, kind of a loose bunch of some cotton candy or something. You put cotton candy in front of a powerful fan, it'll kind of blow off, right? And so those, you can accelerate the winds to, the typical rotation speed around this supermassive black holes, which down in the center, is maybe a thousand or at most couple thousand kilometers per second, which is very high, right? It's a high velocity. However, once you go into this ADAF mode, something even weirder happens. And essentially, due to a combination of the fact that you're sort of bringing in the magnetic fields as you advect the gas can then concentrate the magnetic fields down. And once it starts doing that, it can create a path for things to be accelerated perpendicular to the disk, you see what I'm saying? So basically, as the material advects in, because it's advecting slowly, it can actually carry its magnetic fields and concentrate these magnetic fields into a very narrow channel. And then you get this process known as the Blandford-Znayak instability, and that allows these hot electrons and stuff to be accelerated along the magnetic field, and you end up with a jet. Okay, so this state then gives rise to these very, very high velocity, relativistic velocity outflows. Right? It's kind of weird. So, in fact, this state, and this will be important in the end, this state actually carries more energy than that state, despite the fact that this one carries more material out. Remember, its energy is mv squared, right? So, you know, the fact that you can get this magnetic acceleration results in this state actually putting out more energy than this state. Okay. So, how do we know all this? Well, I won't go into too much of observations, but I just wanted to introduce this idea of a unified model. Okay. So, it is generally believed, although this is, again, there's a lot of controversies and, you know, nitpicking on this model, but essentially, there are many, many different flavors of AGN. So I think, you know, back in the, you know, when I first sort of started learning about AGN, I was like, what are these people doing? Like, every AGN has its own type, it literally. I mean, it was just ridiculous how many subclasses and classes and different names of things they had. So there was then Meg Geary and company, Mitch Bagelman, a bunch of people came up with this idea of a unified model that essentially what the flavor of the AGN, and most of these AGN were characterized by different types looking spectra, right? So these are narrow line radio galaxies, broad line radio galaxies, Seyfert 2, Seyfert 1, there's now Seyfert 1.1, there's Seyfert 1.5, oh my God. There's, you know, normal galaxies, a liner, this is a BL Lacerti object, which is essentially a very has very, very fast outflows. So effectively, basically, it's owing to what your viewing angle is relative to the torus. That's the basic idea of the unified model, is that what you see, what type of AGN you see, depends on which direction you happen to be looking at. Okay. So, you know, these scales are, of course, extremely small, right? They're, you know, well, the inner accretion disk is going to be a sub-parsec, right, way sub-parsec. So we're talking about things very, very, at the very, very centers of the galaxy. But then they create these jets. For instance, here's again, they have the Fanaroff-Riley type 1 and Fanaroff-Riley type 2. These radio jets, you know, you can see whether they have hot spots at the end of the lobes or not. But the point is, like, and this is a very large scales. That was my point. This is a very large scale. This is like, you know, hundreds of kiloparsecs. So what's going on here down at the central inner parsec can be felt out to very large distances. Okay, so this is the basic idea of AGN feedback, right? This is the idea that you can extract energy from very, very close to the black hole and distribute it now over, you know, even not even in jets, even in those radiative winds, you know, 1,000, 2,000 kilometers per second will get out a long way. It's unbound from most galaxies, et cetera, right? So you have the AGN winds, which are, as I described, this radiatively driven off the torus. You can, at high Eddington ratios, and you can see it in a variety of tracers, right? So you can see it in things like H alpha, in O3, and in CO. You can see it in X-rays as well. That's your typical outflow velocities here. So this is, you know, just examples of the maximum velocity observed in one of these radiative outflows versus the bolometric luminosity of the black hole. Okay, so the biggest black holes can get up to, you know, a couple thousand kilometers per second typically, right? So that's one type, right, that occurs at high Eddington ratio, and then you have these low Eddington ratio things where you get these kind of radio jets, right? And so, you know, radio jets are not super common, right? Then they're best seen in the radio. Why are they best seen in the radio? Well, the main point is that everywhere else, it's kind of, every other band, the black hole is kind of overshadowed by the galaxy, right? Particularly in this low accretion state. It's not very bright otherwise, other than when you can see these jets, right? Now, these jets, what do these jets do? Well, they're very high energy, so they create synchrotron electrons. And synchrotron electrons have a power law slope, of course, which means that once you've died off all the other emission from the galaxy, now you can see this power law to very, very either high or low frequencies or energies, right? And so you can see AGN best in the X-ray, right, or these jets certainly, or in the radio. So, the galaxy, the optical light, the stars and stuff don't emit much in either of these, so then these types of things really stand out. Okay. All right, so let's now think a little bit about what these sort of things do to galaxies. But before that, let's bring in one other factor, right? So I talked at the start about morphology and how morphology. Not only do we need to quench the galaxy, not only do we need to grow the black hole, but we also need to change the morphology, right? And we've talked about this before. That I'll just show this nice little video here. In this one. This simulation, they've actually included, it's a very simple simulation, just two disks running together, no cosmology or anything. But they've actually included black hole feedback in here. So this is back from the mid-2000s from Tiziana Di Matteo and company. And it's color-coded by gas temperature, and you see the usual thing that, this formation of bars there for Christina. And what it's doing is, of course, because of the disruption of the orbits of the gas, you can funnel that gas down to the central regions very quickly, and that allows your high accretion rates, which then allows this kind of feedback, which in this case is being just sort of blown out in a spherical wind, right? So this is only showing the gas, and what you see is that, it's kind of hard to see where the two nuclei went here, but basically there's going to be one final dramatic, merger, right? That's going to blow everything out, right? And you're left with this kind of gas-free galaxy, right? Now, of course, this galaxy would have stars and everything like that, and we've seen in previous simulations that the stars would become elliptical, obviously. So this kind of process can clearly drive strong AGN, right? And that's a good explanation for why these kind of things like Markarian 273 exist, where you get a merger with a very strong AGN, and you see this in the demographics that you observe as well. So what's being shown here is, I keep forgetting that things are cut off the bottom here. So this is basically infrared luminosity. So this is in log solar units. So this is 10 to the 11, 10 to the 12, 10 to the 12.3 or whatever. And then this is the fraction showing effectively bright AGN, right, of different types. And what you notice is that, of course, as you go to higher and higher infrared luminosity, which comes from which typically comes from the star formation due to mergers, the big Euler things over here above 10 to the 12 tend to be mergers, at least in the local universe. Then you get this very high incident of AGN. So there's definitely a connection between AGN and mergers, right? So that's very nice. And because of this, I mean, in the old days, this is kind of the thinking of everyone, and it was nicely summarized. It wasn't not invented by Phil Hopkins, but he made the plot that everyone this is the importance of making good plots. Everyone shows it, even though you didn't really have anything to do with inventing the idea, right? So this is from Phil Hopkins' 2008 paper, and the idea, right, is that we want to get both morphological change, we want to grow the black hole, and we want to have a red and dead galaxy in the end. So you start with an isolated disk, then you're in a small group, like Milky Way Andromeda type thing, and then the two merge, you get something like the antennae or something like this, or the mice as it's called here. And then you get the coalescence, right, like we saw in the video, that the two things finally come together and you get a big bright AGN along with the starburst. So what's being plotted here, for instance, is just -2 to +2 in gigayears versus the time of the merger, which is at 0 here. This is the star formation rate, and this is the effectively the tracer black hole accretion. So they computed the bolometric luminosity here in this case. So again, you see this starburst that happens during this kind of phase right here between D and E, and it's accompanied by this big black hole growth. So the two things kind of go together, and you can then end up with the blowout phase, right? This is just summarizing effectively what we saw in the video. You get this blowout phase. For a while, you see kind of a naked, almost naked black hole, right, without a whole lot of gas or star formation around it, as that last little bit is going down into the galaxy and continuing to fuel the black hole, even though the rest of it has been kicked out, and that's your quasar phase. So you see these very, very luminous AGN that typically seem to arise in merger galaxies, so it's a little hard to see here, but you know, HST was able to basically show that most of these things, that if you look in detail at quasars, most of them seem to be in mergers. Not all of them, but most of them seem to be triggered by a merger, right? Again, these are all fairly local, right nearby. Then you have this post-starburst phase, which is a super interesting phase of galaxy formation, often called K plus A or E plus A as well, due to their spectra. Won't talk too much about this, but this, you know, one of the smoking guns. And then finally, a few gigayears later, all these kind of things, all these fate stuff disappears, right? So this is kind of, you know, was the standard scenario, you know, 20 years ago. But, like, pretty soon people started to realize, when they thought about this in a more cosmological context, that this can't really be the way that most black holes grow, okay? So there's sort of two problems with this idea. One is that, okay, you know, the movie shows you can do a great job blowing all the gas out. Fine, okay. But wait a minute, there's no reason that gas can't start coming back in. I mean, we've seen that in a cosmological context. You blow stuff out, even at 1,000 kilometers per second, you know, even if you got rid of that stuff, there's plenty of stuff in the IGM that's still allowed to come in and cool and do all its bad stuff, right? That you don't want, because effectively, you know, you want to quench your galaxies. Your, you know, to big elliptical have been quenched for, you know, typically 5, 7, 8, 10 gigayears, right? So you have to shut off star formation not just instantaneously, but you have to keep it shut off for a long time, and that just kind of doesn't happen. So, you know, what you know, this paper did here is this is just showing some star formation histories of galaxies that, you know, and the black lines are the stellar mass, and the dotted lines are the star formation rate, and these sort of lines here are mergers. Okay, so when we have two mergers, and what they did in this simulation, actually it was my student, what we did in this simulation was that whenever you have a merger, we said automatically, let's suppose all the gas gets expelled. That's the best you can do, right? What's going to happen after that? So it's just kind of a numerical experiment. It's not really a physical model, just sort of, even if we tried this most extreme thing, what happens? Well, what happens, in some cases, you get it pretty quenched afterwards, but in most cases, no. So here's a case here, within about 2 gigayears, you're kind of restarting star formation, right? Here, you have a bunch of mergers, and in each merger, of course, we're you know, cutting off all the star formation because we're literally ejecting all the gas by fiat. But again, within like a gig year, maybe, you restart the star formation, right? So the problem is not only you have to stop star formation, you have to keep it stopped, right? None of these galaxies today, well, at least the top and the bottom ones, will look like you know, real ellipticals today, right? So that was one problem. The other problem is that, you know, mergers are simply not frequent enough, right? Particularly at low redshift, to grow all the black holes we need, right? You know, you can now do simulations. You know, this is comes from the SIMBA simulation, but a lot of other ones do a similar thing, where you can look at, you know, what is the connection, you know, within a cosmological scale. So you can go in your simulation and say, okay, I had a merger there, but now I'm actually, unlike in these old simulations, these ones actually track the black hole growth and figure out, you know, where does the galaxy quench in star formation. What's being plotted here is the time of merger for a particular galaxy versus the time when it quenches. So, you know, we take all the galaxies that are quenched, you know, by redshift 0, that had a merger in the past, and ask the question, you know, what is the relationship between the time when it had a merger and the time when it quenched? And if quenching was equal to merger, right, if quenching resulted in a merger, we would expect all the points to kind of lie, they'll be a little bit after the merger, it'll quench, but pretty much, within sort of, half a gig year or gig year, it should quench, right? We would expect all the points to sort of lie in this little region here. But they don't. You see, they scatter all over the place. Even ones that quench very fast. So this is the quenching time scale. So blue is quenching really, really fast. So like, one time it was quenching, it was right on the main sequence, the next step is just done, right? Whereas these quench over much longer time scales, right? And again, even the fast quenching ones aren't associated with mergers. So when we saw that there was this sort of dichotomy between these fast quenchers and these slow quenchers, first thing we thought, oh, the fast quenchers must be the mergers and the slow quenchers are sort of something else, right? But no, that's actually not how it works either. So, okay, that's just one model. There are many models out there. No one knows who's right. But I think at this point, generally no model in a cosmological context employs mergers to do the quenching and the black hole growth, over to produce your quenched galaxy population. So what do they do, right? Well, it was the idea of a couple of people, Richard Bauer in Durham and Darren Croton in Australia, kind of independently, came up with this idea of radio mode feedback. Now, why do they call it radio mode? Because it's a mode that they said must be associated with these radio jets, okay? So I like to call it jet mode, because radios, you can now see jets in all kinds of things. You don't have to see it in the radio. Other people have called it maintenance mode. When Rachel Somerville did her models, that's what she called it. But it's all is the same idea. What's the idea here? The idea is, again, what we need to do, right, with our sort of preventive velvet rope feedback is to make sure the gas that's outside never cools, right? And if we can somehow keep that gas hot, of course it is going to cool, but if we can sort of counteract that by pumping heat into it, right, maybe we can keep that gas on fairly large scales, on 100-ish kiloparsec scales. If we keep it hot, it will never fall in, and we can starve the galaxy, and it will eventually quench, right? So the jets, of course, are a great way to do that, because you've got something here, you're extracting a lot of energy, and you're depositing it out at, whatever, tens or hundreds of kiloparsecs away, right, in the surrounding gas. So, so that's the basic idea. There's actually observational evidence for this, right, and it comes from these cluster bubbles. Okay, so what is a cluster bubble? So the most famous example is in the Perseus cluster, most famous because it's the most nearby, one that has these really prominent bubbles, so we can study it in a lot of details. And if you look here, so this is the central galaxy in Perseus, right? And this is an X-ray map. It's been slightly processed to increase the contrast. But what you see are these sort of regions around that are kind of depressed in X-rays, okay? And remember, X-ray comes from cooling, Bremsstrahlung cooling effectively, for the most part, although line emission can be important. But effectively, that means that these are, the Bremsstrahlung goes as density squared T to the 1/2. That's a good thing to sort of have in your head, right? So if you don't see emission, if you see low emission, what you think is that it's low density, okay? Might be low temperature, but in point of fact, it's T to the 1/2, so it's not it's much stronger dependence on density. So that means that these are cavities, effectively. These are regions of lower density in the entire cluster potential. So again, this is close to a megaparsec scale across, right? So these are cavities that have been blown at sort of several hundred kiloparsec scales, right? And of course, what happens when you blow a cavity in something? It becomes less dense. You're in an atmosphere, right? It's just like you blow up a helium balloon. The helium balloon goes up, right? And so you see these relic cavities up here, which you think might be associated with older cavities that blew a bubble, and that bubble was like actually buoyantly rising. So you see a number of these different cavities. Now, what was really cool about this was when they started looking in the radio, for instance, right, and they saw that there were these jets. And those jets lined up exactly with these bubbles. So in other words, it's like, you know, taking a straw, literally, or whatever, like, you know, and blowing up a balloon over here, right? You're blowing, you have the energy coming out, and it inflates a cavity over here, right? And you can actually track this process out, and you can ask the question, what is the PDV work done by this blowing this bubble? Because you have to put, you know, it takes work to blow it against this atmosphere. And so you compute, you know, the volume and the pressure, and so you can get PDV, right? And then you compare it to what you get for the cooling rate, right? And you say that basically, well, you know, I have a time scale for how fast these jets are, so I have a time for how long it's taken, so I can answer the question, you know, how much, you know, what is my rate of energy injection into the bubbles? And it turns out to be, you know, at least within an order of magnitude, you know, exactly the cooling rate. So effectively, the heating can balance that cooling, at least sort of in these cases. Now there's many of these cases known. It's a big industry to sort of do these cluster bubbles, right? So, you know, the idea of this then is that, you know, you start off with some you know, galaxy with a big hydrostatic halo of hot gas around it because you're in a massive halo which is hot mode, and then you get this radiatively inefficient accretion, which creates these jets, right, as we discussed. So you can get these kind of jets. And these jets basically result in long-term heating and cooling balance. And what's nice about this is that this can be recurrent, right? So yeah, okay, you know, if you blow the bubble, you inject some energy into the surrounding gas, well, okay, but eventually the cooling will restart again. But as soon as the cooling restarts, right, what happens is some of it feeds the black hole, and it'll put out another jet, right? And that's why you see these multiple bubble events, right? These are this sort of cycle of, you know, the material collapses down, ignites the jet heats the stuff, and then, you know, it stops again, right? And every once in a while you see, and of course that material raining down will form some stars. And in fact, if you look at about 20% of ellipticals do have star formation. So, you know, just that rough number would tell you a duty cycle of around 20% for this process, right? And that's, you know, more sophisticated to give you in that range as well. So this is the idea. So this is the way to quench galaxies long term. Yeah. Yeah. Right. So for one thing, the energy isn't enough. So effectively, you know, the energy is probably off order 5 to 10 times less. Despite the mass being greater, the velocity is, of course, much less than in the jet, right? So that does not give you quite enough energy to balance it out, right? And the second part is, of course, that you know, when you have this radiatively efficient accretion, right? So you can get jets in some cases, but for the most part, you often don't. And so effectively, that means that not only if you get these high accretion rates, you should form a lot of stars, right? So these kinds of radiatively efficient cases usually occur in something like a Seyfert galaxy. And in a Seyfert galaxy, of course, those things are forming stars roughly on the main sequence, right? So it's clear that those things have not, you know, been able to do too much to the disk of stars, right? Whereas all of these things, we never see that kind of disk forming in these massive galaxies for the most part, right? So there's several reasons why you can't appeal to that one. You need the energy, basically. Okay, so what's cool is you can do kind of simulations of this now. Well, actually, this is brand new work that was just put out by my student, but we actually included jets in a cosmological setting, like a full cosmological run, did zooms, kind of basically the first time it's been done, or at least it's been done and it works. But what this is showing here is kind of how this kind of process goes along. So this is a single group size halo that we took out, and we resimulated it. And what's being shown here is the kinetic energy here, and the dotted line is just the black hole mass. But this is the dashed line is, or whatever, the jaggedy line is the amount of jet energy that's being put out, right? And what you can kind of see here at the start is it's really visible here. You can see these bipolar jets. They're inflating these cavities. They don't last for all that long, but you can see them probably best in the projected density, right? They create these sort of cavities around the black hole. What's really cool is that midway through, this one, look, it like changed direction. So, so these jets can actually rotate around, which is why these bubbles don't all sort of line up in something like Perseus, in some big bead, because over sort of 100 million year timescales, you can change the angular momentum of the jet, right? At least in the way we're computing the jet direction. So that's cool. So you can kind of pictorially see what's going on, but then you can go and measure stuff, right? You can go and ask the question: is there enough energy being deposited by the jet to actually quench the galaxies? Because these galaxies are quenched in the simulation. We've kind of, and that's what's being shown here. So this is the power in the cavity. Okay, so this is what Fred has done is basically gone and measured, identified these little cavities using this same sort of machine learning tool that people do with clusters. Go and say, okay, for those particles, what was the PDV work done to inflate that? And I'm going to compare that against the X-ray luminosity. X-ray luminosity corresponds to the cooling, right? That's a direct measure of how fast the gas is cooling. That's why you get the X-rays, right? And indeed, so this would be the one-to-one line, right? This would be heating balances cooling, right? And you can see that, this is really kind of what the simulation is doing, right? Not only that, once you get below about 10, this is the halo mass up here, once you get about below about 10 to the 14 in halo mass, you're actually over-pressurizing relative to what you need for cooling, right? And so at least in this simulation, this is kind of actually what you need, right? Because you need to kind of, not only you need to stop everything and hold it in stasis, but at least at the start, you need to really blow stuff out to begin with, right? To quench the galaxy in the first place. Right, this sort of part will only maintain your quench status. But how do you get to quenched in the first place? You need to really have a lot of energy, and that's what these jets are doing, right? So you can look at this then in another quantity, which is kind of a fun quantity that I think is something that tells you a lot about how this process works, right? So what's being plotted in this set of plots here is, as a function of halo mass, we're going to plot the total fraction of baryons in the halo. And we're going to divide those baryons into various phases, right? So the blue part is the stars, okay, that's some of the baryons, right? Then we have the interstellar medium, the winds, stuff that's being blown out right now. And then you have various phases of the circumgalactic medium, right? So this is the hot phase, the little purple stuff here, right? Now, the cool thing about, well, one of the cool things about Simba is that we have all these models where we turned off all the feedback processes one at a time, just to see what happens. Pure numerical experiment, right? That's the fun thing about simulation, do these numerical experiments. So you start without any feedback, right? And of course, if we don't have any feedback, there's no reason the baryon should go anywhere, right? You should basically have your cosmic fair share of baryons, which is what this one designates. So this corresponds to the baryon fraction divided by 0.16 effectively, right? So this is this cosmic fair share baryon. Sure enough, with no feedback, that's what you get. No surprise. You add star formation feedback, just turn that on, nothing else, and you can suppress the low mass halos below about 10 to the 12, right? And so you're actually ejecting material out of these low mass halos. Here we had a hugely gaseous ISM in these low mass galaxies, right? Way too many stars, by the way. That's overcooling, right? So you see this number of stars, ridiculous. So that's just overcooling there. But you've lowered the ISM, which means you lower the amount of star formation, and you preferentially do it to lower masses. Good. That's exactly what we wanted, right, from last time. Now you add the AGN jets, and all hell breaks loose, right? So basically, the AGN jets don't appear until you get, sufficiently massive black holes, so they don't really change this part of the curve much, this very low mass end part of the curve. But everything else, they really blow the heck out of it, right? They've essentially ejected all this gas that was here out of the halo altogether. And this is it's effectively these jets, right? These are the jets overpressurizing the gas and actually evaporating it, right? And so, and as you can see, that means that one of the big things that this particular model predicts, and in fact pretty much most models predict that do this, is that look at the baryon fractions in these halos, right? They're very, very small. There's only about, the halos around the Milky Way, or, well, just above the Milky Way, type of thing, in these small groups, only have about 10% of their baryons left in gas, another 10% in stars. That's it, right? So, there's always been this sort of missing halo baryon problem. You might have heard of this, right? And people said, oh, maybe the baryons are in some weird hidden form that we can't detect, and we have to look in this band and that band and this absorption line. Well, according to us, they're just not there. So don't bother, right? And so you can sort of see from this, again, how this translates into shaping this cosmic star formation efficiency. You get this kind of peak here, maybe a little bit less than 10 to the 12, but right here. But then above that, it's quite inefficient at forming stars, and below that, it's more and more inefficient at forming stars. So you get this. So we can now sort of put labels on this plot. I showed this plot last time, and I just said it was feedback. But here we can now tell that this part is star formation feedback, and this part is the AGN feedback, right? And it kind of sets that curve. Yeah. Mm-hmm. Yeah, so like 10 to the, yeah. Yeah.
Some of it might also be that you're talking about larger and larger volumes, right? So you're integrating over a volume where the gas may be just hanging around there, but it was completely expelled from the galaxies.
Yeah.
This was happening, right? Or
yeah, well, okay, so this is the total baryon fraction in the halo, not just in the galaxy, right? And it's true. So if we extend this, I mean, in other simulations, bigger volume simulations, this does extend up. That's just because it's effectively the same thing with a binding criterion, that the jet energy that we're putting in, we're putting in kind of a constant jet energy because we don't know what else to do. And so, we basically say that's our constant jet energy, which means that in a very big halo like a cluster, that's sort of marginally escaping, right? It's not really, whereas in something like a 10 to the 13 solar mass halo, it blows the heck out, right, without any problem, right? So that's all that is, but this is actually can be a measured quantity, sort of above here, the fraction of hot baryons just from the X-ray emission, right? And for instance, this model and several others like TNG and stuff agree with it reasonably well, right? Okay, so this is kind of a little bit of an aside, but this is a very fun story because it really sort of illustrates how crazy this connection is between what's going on at incredibly small scales and what's going on larger scales. Okay, so there's essentially, well, I've showed this sort of cosmic star formation efficiency, which is the stellar mass divided by the halo mass versus halo mass. Let's just talk about stellar mass versus halo mass, which is mostly a linear relation, but it has a bend over, right? So essentially, it's something that kind of looks like that, right? It's mostly linear, of course. Bigger stars, stellar masses, live in bigger halos in general. Okay. Well, it turns out people tried to go measure this quantity, the stellar mass and the halo mass. Well, now, okay, stellar mass is easy, relatively. How do you measure a halo mass? Well, there's kind of two main ways to do it. One is to use the dynamics of satellite galaxies, right? So basically, you get just a simple dynamical argument. That was done by Surhoud Moret, which happens to be these red and blue lines here. That's the red and blue curves here. And then there is essentially another way to do it, which is more recent, which is weak lensing, right? So you can actually measure the total mass enclosed by weak lensing, right? And get the halo mass that way through some extrapolations. And that was done by Rachel Mandelbaum and company. Now, when people started to do this, what they saw, right, was a very clear trend that at a given stellar mass, the blue galaxies, so the sort of the green points here, or the blue curve here, the bluer galaxies tend to live in lower mass halos, okay? So bluer galaxies live in lower mass halos, red galaxies live in more massive halos. Now maybe you think this isn't too surprising, right? So you say that, well, okay, if you're a quenched galaxy, you must have grown very early, right? So you grew the galaxy very early, it went through, got a big black hole, quenched itself, and now it doesn't exist anymore. But it still kind of has a leftover higher halo mass than something that's kind of growing more slowly. So in that scenario, the red galaxies, these galaxies, should be in the early formed halos. The quenched galaxies today should be the things that formed early in the big halo, and then, you know, even for the same halo mass today, you know, they form most of their halo early so that star formation could proceed and stuff. Okay, so that would be a test of whether that scenario is true, and it turns out it is completely flipped. Okay, so here's a plot of the halo formation time versus the stellar mass. Okay, and you see that all these galaxies up here, which are all the red galaxies over here, right? This is the same plot, just now effectively color-coded by halo formation time. They are at the higher halo mass. So wait a minute, what happened there, right? So now these red galaxies are living in the late formed halos, and the blue galaxies are living in the early formed halos. Weird. Okay. You can define this thing called a formation time, which essentially is a star formation. You can think of this as kind of the what this author called a transition time. This is actually a Nature paper that we put out. So effectively, what happens is that these galaxies, these late formed halos, had you can think of this as a quenching time. That's really the right way to do it. This is the time when the galaxy's quenched, right? So these galaxies, they quenched early on, right? So there's an inversion between this quenching timescale and the halo formation timescale. How does that come about? Okay. And it comes about effectively through the following. I won't go through all the arguments, but basically what it is if you have an early formed halo, okay, so you get a bunch of halo that happens to form earlier for a given mass, it accumulates a whole bunch of cold gas very early on, right? Because back then the cooling times are very fast, you can gather a whole bunch of cold gas, right? Which means that, remember, the jet mode is triggered when you have low accretion rates, right? So as long as you have high accretion rates, as long as you have a lot of gas around, you're going to stay in this radiative mode, right, which does not give you enough energy to quench. So in point of fact, the jet occurs later, which means the quenching occurs later, which means that you have a bluer galaxy, right? So that's the sort of argument that we tried to make, right? And in point of fact, most models get this wrong, get this prediction wrong, okay? So because effectively you have to have some kind of model for black hole feedback that puts out more energy when you have less accretion, which is weird if you think about it. You would think, you have more accretion, you should get more feedback energy, right? Well, that doesn't work. That actually ends up giving you the wrong answer, right? So that's really where it comes from, and I just think it's fascinating because essentially, stuff that's going on less than parsec scale is, because of the way that accretion disks work, is impacting the global galaxy population. So it's kind of fun. So another way you can try to see this type of feedback in action is to use the halo gas, right? So you can go out and try to observe what's out there in the halo. So I've talked a little bit about the X-ray bubbles, but you can also think about other sort of profiles. For instance, the electron density profile, the temperature profile. This is the pressure, and then this is this funny quantity called entropy, which X-ray astronomers like to define. It's defined as the temperature divided by NE to the 2/3. And if you work that out, that happens to have units of entropy, although it has very little to do with, what you would, as a physicist, call entropy. But it does have the units of entropy. And that turns out to be a very instructive quantity, right? So again, this shows a comparison of a bunch of models. So from Ben Oppenheimer's really nice review article. And what you can see here is different models make very different predictions, and here's all these observations of each of these quantities from various sources. And you look at, like, for instance, something like Simba, it's like, well, this is great. Simba blows out all this gas and stuff like that, but it seems to blow out too much gas, actually, if you start to compare to observations, right? And you see this, it's over-pressurizing the graphs, right? Or, because it's T divided by N to the 2/3, you get too much entropy. But even more than that, right, what's weird is pretty much every model, so Eagle, TNG, and Simba, Eagle does not blow out very much gas out of the halo, so you can see much lower entropies, but you still get the shelf. And this shelf is basically a feature of, seems to be, at least that so far as we can tell, a feature of any model that successfully quenches galaxies. Romulus, which is this one, does not successfully quench its galaxy, right? So this is, at the moment, kind of a big mystery right now, right? And the reason you have that, of course, is because you have to sort of keep the gas hot right in this regime. This is a few hundred kiloparts. This is where the jets are depositing all the energy, et cetera, or whatever feedback mechanism you're using, right? This is where the energy has to get out to and counteract the cooling, and that creates a flat entropy profile. Otherwise, the gas will just continue to rain down in and continue star formation, and then that's what happens in Romulus, right? If you allow the entropy to just, be lower and lower, it will just cool down. So that's not so good. That's a bit of a mystery. I think we don't have a good answer as to how to reconcile these two issues. You have to heat it, but you have to heat it in a way that somehow preserves this entropy profile like that. Yeah, okay. So, the other fun thing is to look at something like the X-ray luminosity versus the stellar mass. So this is another quantity that can be measured. So what Anderson and Bregman and company did in 2015 is they took ROSAT and they looked around a whole bunch of galaxies, and around each galaxy they basically stacked within bins the X-ray luminosity in each case, right? And so those are those black data points here, and then you can do the same analysis in Simba, and it looks very good. But what's interesting about this is now in Simba, you can also go and color code or look at the specific star formation rate. Now you might think, oh, the hot gas should have a lot more X-rays, right? The hot gas, should be bright in X-ray and so on and so forth, and halos that have a lot of cool gas, which are still star forming, will not have as much X-rays. In fact, it's exactly the opposite, right? It's the star-forming galaxies that have high X-ray. And why is that? It's because the effect is not the T to the is not the T to the 1/2. It's really coming from the N squared, right? And in order to quench a galaxy, you had to blow out the gas, so your gas density is lower, and that creates your lower X-ray emission. So once you sort of have this intuition in your head, you can kind of piece all these pieces of observations together, and individually you might, you don't know what's going on here when you just see the thing a priori, but then you can see it in action. Okay, so another probe, which I'll just mention now. How many people have heard of the Sinyaev-Zeldovich effect? You know what that is? Okay, not that many of you. Okay, interesting. So effectively, it's a effect that you see in the cosmic microwave background. So imagine a cosmic microwave background photon is going towards us, minding its own business, not doing anything. Suddenly, it encounters along the way a galaxy cluster or some big patch of hot gas. So that hot gas is then going to, effectively can occasionally hit a photon or as it's zooming around. And when it does that, because the gas has a lot more energy than the photon gets upscattered, right? The photon gains energy, right? That's the Sunyaev-Zeldovich effect. And it results in basically a shift in the CMB, in the peak of the CMB, where you see, but only in that little region of the sky. And with Planck, now we can actually measure this, right? The older ones didn't have enough resolution to see to resolve galaxy clusters. Even Planck doesn't. It's more like you resolve, 3 or 4 virial radii of a galaxy cluster. But still, you get close, right? So you can make these Sunyaev-Zeldovich maps. And that, of course, again, now what's interesting about the SZ effect, do I have the, yeah, I have the equation here. The entire measure of SZ, what is it measuring? This is the thing to remember, right? SZ is measuring the integrated pressure along the line of sight. That's what it measures, right? It's N times T, right? The rest is just constant, right? So this is basically telling you where the high pressure gas is. Well, what's interesting is the X-rays, of course, right, as I just told you, are mostly N squared T to the 1/2. So they have a very different dependence on N and T, right? So in principle, combining SZ with X-ray, you can disentangle this sort of effect of N versus T, right? SZ telescopes are now just starting to get good enough to do this, right? With the next generation, there's this one big one called Simon's Observatory that's coming around pretty soon. So that's very exciting. I just wanted to introduce that idea to you. What's also cool about AGN feedback, it's at very large scale impacts, right? So one of the things you can see here, so here's again 2 simulations, one where we turned off the jet feedback, another where we left it on. And what these are temperature maps, just projected temperature slices in the simulation, right? And look at the difference by redshift 0. Holy smokes, right? Jets, this is 50 megaparsecs across, 50 H inverse megaparsecs. So about 77 megaparsecs across. So these jets are not just blowing out the stuff right around the galaxy, they're heating all kinds of stuff out there in the intergalactic medium. And so one fun thing you can measure is this so-called closure radius, right? And there's a paper from Daniele Sorini, but there was another one by Iromlu that looked at this in TNG as well as SIMBA, comparing to it. What this is you can ask the question, how far out do you have to go to get back to your cosmic fraction of baryons, right? Remember I told you that we've ejected 80% of the baryons. Okay, well they can't have disappeared. They have to go somewhere, right? They have to go outside, right? So how far out do you have to go, right? And the answer, at least in SIMBA, is ridiculous. It's something like 20 virial radii, okay? So this has a huge impact on, on moving gas around in the universe on very large scales, right? Just to show you, this is a cool movie that shows you 4 different models. This is Illustris, SIMBA, Astrid, and Magneticum. So just 3 other ways of doing these black holes. Look at SIMBA's nicely bipolar black holes, jets. Fun, right? All these kind of crazy things going on, right? Look at these guys, the way they implement feedback, much more spherical, okay? So we're the only one who kind of does it really in a bipolar way. So does Horizon AGN, but they don't quench galaxies all that well. But all the other ones do it much more spherically. It's much easier to quench galaxies with less energy, right? If you do everything spherically, you can heat up the gas in a sphere much easily than trying to do this and then do all these things with the cavity and pressurize and this and that. You just heat it directly if you do it spherically. So it requires a lot less energy than this, right? So you see by redshift 0, this looks completely different than any of this, which is weird. You would be able to think you could observe this, somehow, this difference. Turns out it's really hard, and some things actually agree with this and some agree with that. Anyway, I just wanted to give you an illustration that this is one of the big uncertainties right now in galaxy formation model. How does AGN feedback work all together, but also what are its larger scale impacts? Speaking of larger scale impacts, since we have some cosmologists here, I thought I'd give it an update on this S8 tension problem. Okay. So remember the first day I talked about this S8 tension, which is the tension in the amplitude of the power spectrum. And I also told you that AGN feedback really moves a lot of gas around. Now, sure, baryons are only 1/6 of a mass, but if you're trying to make percent level predictions, 1/6 of the mass is not trivial, right? You have to know where it goes. And so what this is plotting is the power spectrum, right? Just the power, remember the matter power spectrum I told you about earlier, as a function of, let's say, scale here, in a variety of models relative to what would happen if you only had a dark matter simulation. So if we forgot about AGN, no AGN feedback, right? It's just dark matter. And what you see is that essentially the power is lowered on these kind of intermediate scales. So this is, well, okay, you have to multiply this by 2 pi to actually get a physical scale. So it's like 6 megaparsecs. So this is like 6 to 10, 20 megaparsecs. There's a real suppression in the matter power spectrum just from AGN feedback. All of these models include AGN feedback. They just include it in different ways, right? There was a paper recently by Alexandra Amen and George of Sathieu that said, hey, I can reconcile this SH tension altogether if I'm just allowed to play with the power spectrum due to AGN feedback, right? And ask the question, what do I need to reconcile that? And that's the black line here, okay? Now, you can see that most of the models lie well above that, okay? There are a few models that get close to that, so roughly it's in the same regime as this Illustris model here, which does a terrible job of matching galaxies, but the old Illustris model. But in terms of this, it actually does okay. I don't know if they kept the same color code here. I think that's actually this line. But in any case, it appears that at least if you wanted to reconcile the SA tension purely based on this, you would need very, very strong AGN feedback. And in fact, we can reconcile a fair bit of it with AGN feedback. So maybe that one, the Hubble tension is a different question. That's a completely different measurement. But at least this one, maybe AGN feedback is at least part of the answer. Mm-hmm.
Is it the matter power spectrum or is it the galaxy power spectrum here?
Yeah, this is a matter power spectrum. This is the matter power spectrum, not the galaxy one. Yeah, because it's measured from weak lens. It's essentially what you would get for a weak lensing measurement, right? So this is essentially the weak lensing people are very concerned about this. Okay, well, in the last sort of few minutes, I wanted to sort of switch gears a little bit because, of course, we want this lecture to be about quenching, but so far we've really only talked about central galaxies, right? Big, massive ellipticals, so on and so forth. They're not the only things that we see in the universe that are quenched. In point of fact, a large number of satellites are quenched. And you can see that observationally. For instance, you can see that this is the quiescent fraction or quenched fraction as a function of stellar mass. And these are the central galaxies here, and then these are the satellites, right? So you can see that these low-mass satellites particularly, seem to be a lot more quenched than an equivalent mass, low-mass central. So just living in somebody else's halo seems to have had a big impact. Now, that's not terribly surprising. We can think of many other processes that can impact something that's a satellite that wouldn't affect a central. So one of those things is, of course, some kind of tidal process, right? So this is a famous example of a pair of galaxies, UG 1810 and 1813, that are interacting, and you can see that this companion has been tidally distorted, right? And eventually what's going to happen is that all those material is going to be stripped off. Now, you're only seeing the stars here, but imagine what happened to the dark matter halo and all the gas around it, right? That's probably already gone, right? And we're just now starting to see the very center of the halo be disrupted, right? So that's one way to sort of get rid of the gaseous reservoir that you have in your halo. Another way is to simply strip out the gas directly, so that's ram pressure stripping. So there's a lot of talk these days about these jellyfish galaxies. So you see these in galaxy clusters, right? What a jellyfish galaxy is, essentially you see a galaxy, and then you look for the gas. You look for typically H1, but you can also look for molecular gas or even star formation. And you see that there's a big tail of this stuff behind it, right? And this is just, literally just, stripping out the gas as it moves through the ambient medium, right? So that's ram pressure stripping. again, things to keep in mind, right? The tidal stripping goes as 1 over r cubed, so you have to get really close. It's a tidal force, just like Earth, Moon, etc. So it's 1 over r cubed. The ram pressure stripping is rho v squared. Okay, so it requires high velocity to work, which means that it's more effective in something like a galaxy cluster where you have your velocity dispersion is 1,000 kilometers per second versus something like the Milky Way, where velocity dispersion is 200 kilometers per second, right? So that's a big difference in v squared. So generally, they're both processes stronger near the central galaxy where you have more dense gas, you're moving faster, and they're stronger at low masses where essentially, because you can disrupt the stuff much more easily. It's less bound, right? So again, you can sort of, this is, well, I won't go into all these detailed surveys, but they're basically all showing the same thing. So one of the interesting questions that's gotten a lot of attention in recent years is how fast do these satellites quench, right? So you imagine they fall into a halo, right? They're nicely, happily living their best life, and suddenly they're subject to all this other crap because they're now in the environment of a more massive galaxy. So one of the interesting things that has come out of observations, and it was actually predicted earlier, but people were sort of like, okay. People sort of thought, well, okay, as soon as the galaxy comes into another halo, let's say a small galaxy falls into a galaxy cluster, suddenly it will just start to get stripped, and very quickly everything will disappear, and it'll just quench, right? And so the early semi-elliptic models assumed that. That didn't match observations at all, right? And what people realized is that in order to match observations, what you need is what's come to be called a delayed then rapid model, okay? So what does that mean? That means that as soon as a galaxy comes in to a bigger halo, it doesn't even realize it's in a bigger halo for some period of time. It goes on star forming, doing whatever it was for quite a while, right? Before it actually realized, oh, I'm in something that's supposed to be stripping, doing all these things, right? So why is that? Well, because it's not even that surprising when you think about it. You have to strip off all the gas, all the gas in the halo that it came in with, right? So the stripping process, is kind of coming outside in, right? And that takes time. And I think what people hadn't realized is how, at least observationally, it seems to take quite a lot of time. So this is some work from Andrew Wetzel, which kind of invented this whole delayed then rapid thing. What this is the delay time, right? So that's how long does it go before it even realizes it's in another halo, versus what they call the fading time, right? Or the quenching time, which is, how long does it take to go from there to being quenched, right? And you see that the delay time is quite large. It's like a few gigayears, right? And this is versus the stellar mass of galaxies. So what they had to do to compute this, they had to construct a whole sort of a model which says that, okay, I can know the typical orbit of a satellite, from n-body simulations, so on and so forth, and therefore, bootstrap that. So it's not something you can measure directly, but you can infer from observations plus dynamical modeling in the simulations, right? So essentially, this is a very interesting quantity, right? To sort of think about, understanding satellite quenching. Now, another thing that you can look at is, okay, this was for star formation rates, right? You can also think about the H1. Why is H1 interesting? Well, H1 is interesting because it tends to be much more diffuse, right? It tends to be living in a larger region around galaxies. The gas inside the galaxy tends to be dense enough to convert to molecular, so the H1 extent is much larger. Which means, in principle, the H1 should get stripped off first. So we should have less of a delay time for the H1 than you do for the stars, for the quenching. And in fact, that's what you see. So this work by Kyle Oman looked at H1 from alfalfa along with SDSS to measure the specific star formation rate. And you see these delay times are actually quite small. In fact, for the largest clusters, the H1 effectively gets stripped immediately. Or alternatively, way to say it is the H1 was already stripped before it gets into the cluster. Okay. So it all kinds of hangs together, but I think that it's important to keep in mind that there's this very long delay time. This is a fun plot because it's just ridiculously crazy and busy. But I like it because it kind of illustrates every possible scenario for satellites, right? You have sort of gas stripping and heating, and then you over-consume the amount of stars, so you kind of, here you have some delay time. So this seems to be the most common channel delay. Then some delay time before it just consumes its gas. You could have, in principle, mergers or interactions as things fall in, so on and so forth. So you could have delay times outside the cluster, right? Not necessarily inside the cluster. So on and so forth. So there's many different ways to do it, but essentially, so I think it's really interesting to think about which of these are the dominant processes, and what is the interaction, particularly outside the cluster with the large-scale structure before it even gets in. Because I think one of the things that's become clear is that many galaxies, even satellites, are quenched before they even get into any group or cluster, right? So how did that happen? Where was the physics for that, right? Another sort of key concept that people often talk about in terms of satellite quenching is this idea of, so now this is bringing back the centrals into the mix, this thing called mass versus environment quenching. Okay, so what does that mean? So it was noticed observationally, this work from Peng and Lilly in 2010, that what they're plotting here is the overdensity of galaxies. So these are clusters up here, and these are field or void situations down here, versus the stellar mass of the galaxy, and the color coding is what fraction of those galaxies in that little region of space are quenched. Okay, and what you notice is that you get quenched if you're either at high mass, right, or at high density, right? High mass at any density, or high density at any mass. And so that's observationally well determined. And so the way they interpreted this plot was to say, okay, there's kind of two quenching mechanisms, right? There's one that quenches you when you get to high mass, presumably associated with central galaxies with these big black holes and all these things we've been talking about. And then there's another process which corresponds to the environment, which all these satellite processes that we talk about. And indeed, most of these galaxies up here are satellites, these very high, dense things at low mass. In point of fact, it's not obvious that they're two separate things. In fact, both of them can be tied back to just the halo mass, right? So again, this is a simulation that was done a while ago now, where effectively we had some simple model for heating the gas, in halos, et cetera, and sure enough, we could reproduce this plot exactly of this red fraction versus overdensity versus stellar mass. So, this kind of rainbow-type shape. What you can then do is ask the question in the simulation, you can ask the question, where are the big halos? Where are particularly the halos with these hot gas fractions greater than a half or so? Now remember I told you, so effectively hot mode halos, right? So, and remember I told you that hot mode halos occur above about 10 to the 12 in solar mass, so you could equivalently do that. And the thing is that you get this exact same pattern if you make that selection, right? Which then tells you that basically both of these things, right, come from, both the mass and environment quenching come from the fact that you have hot halos, right? And in the hot halo, you either quench the central, through this kind of bubbles, X-ray bubbles, et cetera, or you quench the satellites, because now when you have a hot halo, there's a smooth distribution of gas that you're sort of moving your satellite through, right? Okay. So that was kind of it for this lecture, for today. Again, just to sort of recap, black holes are found within most galaxies of any significant size. They release lots of energy. And I think that effectively AGN feedback is currently the only way we theorists know how to quench galaxies, right? We don't know of any other way that really works to get the galaxy population that we see. Maybe there is another one, but no one's thought of it yet. It can drive a burst of star formation with the mergers and black hole growth, but the problem is that only quenches things temporarily, right? And so we need to offset halo cooling, and that comes from putatively, both observationally and in simulations, it seems that jets can do this, right? And but depending on exactly how these jets do it, you can have a really big impact on things like, you know, the weak lensing matter, you know, cosmological parameters, which is just crazy if you think about it, right? No one thought that they would ever have to worry, you know, cosmologists were like, oh, these galaxy people, they're just a bunch of points, you know, who cares? We just trace things and everything's fine, right? No, in point of fact, you know, this is probably at this moment the limiting factor in getting all your Euclid billion-dollar telescope and analyzing that data and coming up with cosmological parameters out of it, right? This is, I think, the limiting factor at this point is our lack of knowledge of this. So, yeah, it remains very uncertain. And then, of course, you have the satellite. In addition, you have the satellite stripping processes that result in galaxies quenching either at high mass or at high overdensity. And you pretty much have this very nice sort of diagram that comes out of that. Good. Okay, we'll stop there.
All right.
Hi, thanks for the very nice talk. I guess going back to the very beginning of your talk, I was curious what attempts to like theoretically interpret these empirical scaling relations look like.
These, sorry, what?
The empirical scaling relations, so like M sigma, like in light of accretion and feedback models, what do attempts to actually physically interpret these
That's a
look like?
very good question, and I didn't cover that at all. But this is very I can just write something very quickly. Okay, so. Effectively, you know, when people first started modeling galaxies, they thought, oh, how do black holes grow? You know, scratch back, think what did I learn, you know, back in the grad school or whatever about way that black holes accrete. Aha, Bondi accretion, right? Bondi little thin Hoyle. So in Bondi accretion, okay, I won't put in all the factors here, but roughly, Bondi accretion scales as the black hole mass square. What is Bondi accretion, for those who don't remember or haven't taken that? What it is you imagine that there's a big hot halo with some velocity dispersion, sigma, right? And you have a black hole that's moving through it at some velocity v. And as it's going through, it gravitationally pulls in the gas around it, okay? And so you have to, once you get within the gravitational capture, you know, assume that it accretes. Okay, fine. This, of course, is a very steep scaling, which means if you just allow galaxies or black holes to do that, you don't get this scaling, right? You would get something that the big black holes, right, it goes as m black hole squared, which means these things have a huge accretion rates compared to those, right? And so that does not put you on the scaling. So theorists are like, ah, damn, well, okay. But we can fix this. Feedback. Feedback fixes this, right? And so this is several papers long ago, analytic by Joe Silk, that said, oh, but as the accretion rate goes up, you release more energy, and because you release more energy, you then are able to counteract this and magically lie along the relation. Okay, so all the models that I showed you, basically, you know, that are concordant, all reproduce that. So it is possible to do that. But then, you know, some people, namely me and my students, started talking to accretion disk people, right? And they're like, well, this is stupid. We know black holes don't do this. The way that black holes accrete, right, is essentially in a disk. And the main limiting factor of that is that you have to lose a heck of a lot of angular momentum, right? Because you're in a rotationally supported disk out here, and if you want to get that into there, that's a huge amount of angular momentum you have to lose, right? Where is that angular momentum going? So, so that's actually the hard part, particularly if you want to grow black holes at the same time as star formation. Because if you know that the galaxy is star forming, it's going to be a disk, right? So if you think the black holes and the stars are growing together, most likely the black holes, and that's what we find in our models, most likely the black holes are growing in disk galaxies, right? Not in the big ellipticals. And that's where the accretion rates are high too, right? This fast cold mode accretion. So then there was this model that Phil Hopkins again and Elliot Quadrant came up with. It's a massive 60-page paper. You should go through it one time when you have a free week. But it's really brilliant. So they basically work out a bunch of tidal torques due to disk perturbation. So suppose you had some perturbing thing, and you go through the modes and ask how much stuff will actually be perturbed out of its orbit and fall into galaxies. Then they run a huge number of extremely high-resolution, non-cosmological, like sub-parsecs resolution simulations, and showed that there was actually a reasonable scaling relation that you can come up with that describes how angular momentum loss can feed this. And the key result out of all of this is it's basically almost insensitive to the black hole, right? It's to the power 1/6, roughly. But it is very sensitive to things like what fraction of your gas is in a disk, or what is the mass of the disk? I forget exactly what the scalings are, so on and so forth, right? So effectively, in this thing, right, the galaxy and the black hole, the black hole and the stars are kind of growing together, and there isn't a whole lot of difference between them, because this stuff, right, is also where the stars form, right? So in this model, essentially, you get kind of a one-to-one relation between the stellar mass and the black hole mass. So that's kind of basically what you see, right? The problem is, right, that it doesn't account for this bulge thing, right? That the black holes, particularly as you get to low mass black holes, right? It's tracing the bulge, not the total stellar mass of the galaxy, right? And so that's a more difficult thing to achieve. Now, the way people have thought about doing that in recent simulations is people noticed in simulations that when you're down at these very low masses, you have these very high specific star formation rates. And I showed you some of these movies that early galaxies are very irregular, and they're like lots of supernovae and stuff like this, right? So these early galaxies have a very hard time, setting any kind of a disk-type configuration, which you can then funnel down to the black hole. All the gas gets blown out before the black hole can even form, right? So the explanation for this part is actually that it's suppressed due to star formation being able to blow out the galaxy before it can get into the black hole, right? So this combination of thing also works, right? So both of these models work, but they actually have quite different behaviors on other things than this plot, but both of them can reproduce these plots. But I think it's a really interesting question to ask, which of these is the dominant mode in what regime, and if maybe one or both are just not relevant at all.
Thanks, Romeel, for the lecture. Could you please go back to the slide where you showed the time to merger and the quenching?
Right. Come on.
Yeah, that one. Yeah. So, if I may ask, like, what is the mass regime of this quenching? This quench, like, which mass we're talking? Like 10 to the 12, 10 to the 10?
So these galaxies all tend to quench sort of around basically Milky Way type masses on average. So generally in these in pretty much all simulations, you have to have the quenching occurring right between sort of 10 to the 10 and 10 to the 11 in solar masses. And that range is basically which ones quench earlier is the ones with happen to have the bigger black holes, roughly. That's kind of how it works.
Yeah, so that's what I'm thinking, right? Because at high masses, then, AGN feedback can have like a really, really big impact. But what about low masses, right? Like 10 to the 10, 10 to the 11. So have you guys looked into, I don't know if this is your work, but like, have you looked into any morphological transformations regarding quenching, because we, as far as I know, we still don't know like which causes which, right? If we quench because we're morphological transformation, or we are morphological transformation because we are quenching, right?
Yes, right.
So could you comment on that?
Yeah. Well, that's obviously a very interesting question, and why red disks are interesting, right? It's exactly this question. That's right. I think the consensus is that it's at least a lot easier to arrange that the quenching happened first and then the morphological change, because one thing that you don't see a lot of is big blue ellipticals, right? You see red spirals, not many, but you see them. right? Big blue ellipticals, it's hard. I mean, you do see ellipticals that have star formation, but typically their specific star formation rates are still well below the main sequence, right? They're not like, because for instance, a coma cluster, you know, the central galaxy should, well, let me think, not the coma, well, Perseus. Perseus is a good example. So the central galaxy in Perseus has a star formation rate about 150 solar mass per year. You think that's huge, right? But you then compare it to the stellar mass of that object, and you realize it's still pretty far below the main sequence, right? Or at least an extrapolation of it. So, so yeah, I think that's I think the general consensus is that the quenching, if anything, has to happen first. But in terms of actually figuring out, you know, statistically whether it works, I think that's an interesting constraint on these models, because different models will make different predictions for that.
Thanks for the talk. I would like to ask that how frequent are jets observed in galaxies, in AGNs? Because you said that models can only reproduce our problem with the mass if we use the feedback agent,
Yeah.
but how frequent is observed?
Right, good question. The answer is, so the canonical answer used to be 10%. Whenever somebody would answer that question, they would say 10%. That's what all the radio people would say. I don't think it's that simple. Well, in fact, the latest radio data is not nearly that simple. So it's basically a strong trend with mass, and I'm trying to think what the numbers are on this thing. So this is F of radio loud, or F above some radio luminosity, you know, L 1.4 gigahertz or something like that. And, you know, at 10 to the 11, you're at sort of, if I remember, it's something like, you know, 10 to the 10.5, you're at like, you know, a few percent, and then you're going up to like 10 or 20%, and then by the time you get to really massive galaxies, it actually approaches close to 1, like well above a half, right? So it is actually a strong function of mass, but those are of course just the radio AGN. But those are probably the jets, right? So yes. So it's a good point, right? So I think the point you're making is a very, very good one, which is that the simulations require jets to be everywhere. Do we actually observe them to be everywhere? The answer is no, right? On the other hand, jets are intermittent. I mean, we saw in that one particular movie I showed you from our simulation, that happened to be a case where there was a jet, and we particularly looked at the time there was a jet. But if you ask the question, how often would we see jets in a halo like that, which is around 10 to the 13.5, the answer is 5 or 10%, right? So we don't see them in every halo. But again, you know, you can still, all you have to do is heat the gas up, and then it's going to take a while for it to cool down if you raise its entropy enough, right? So that's kind of the idea, right? But it's a very interesting constraint to see if you can match this. And in fact, our simulations kind of mostly do, but not quite. There's some interesting discrepancies. Yeah.
More questions?
Lunchtime.
Okay, so let's break for lunch, and we'll see you back here at 2 p.m. All right, thanks, Romeel, again.